The good thing about functions with two variables is that you can graph the function in three-dimensional space, and you can think of that graph as being a surface in three-dimensional space. In that sense, you can think of a tangent line at a point on that surface as being the best fit line in a given direction. So if you're doing a partial derivative in the direction of, say, x, the tangent line would be the line that's parallel to the x-axis, or at least going in the x-axis, but also could be slanted up or down according to the z-axis. So the partial derivative has something that makes visual sense. It's the slope of that line. Similarly, if you do the partial derivative with respect to y, you can see that as being a line in a line perpendicular to the x-axis going through the point, and best fit to the surface as a slice inside a copy of the zy plane, or a trace of the zy plane. So we can take partial derivatives with more than two variables, or functions that have more than two variables. The problem is we can't visualize what that function looks like because it requires at least four-dimensional space to see the whole graph. However, we can still understand what the partial derivative is telling us and how to compute it. If you remember what the partial derivative was telling us in the two-dimensional case, it's saying that as you change your variable in only the x direction, what is the response change of the output of your function? That would be the partial derivative of your function with respect to x. If you do it with respect to y, you're looking for the difference ratio or difference quotient that responds to a change in just y. What is the output change going to be? If you had a function of a third variable z, you can then reason the partial derivative with respect to z is going to be how does the function output change if you only change the z variable input. In practice, when you're doing partial derivatives of, say, an extra independent variable like a z independent variable, you compute the partial derivative in exactly the same way using the exact same kinds of derivative rules. You don't need to visualize what it looks like to understand what you're computing, though. So in the book, it asks you to do this example of computing the partial derivative of this particular function, and we certainly can. But I want to give a story to this function just so you can understand what it means. Now, this isn't a real model for the growth or the height of the plant can grow depending on these parameters. It's just a story I made up so that you can get a sense of what the partial derivative is telling you in terms of language. So I want my x variable to represent the intensity of light received by the plant per day. I want the amount of fertilizer mixed in the soil to be represented by my y variable, some sort of number, and my z variable to be the amount of water received by the plant per day. Again, I'm not worried about units because this is just a story to go with the problem, so you can put words to it, or so you can put meaning behind the partial derivative. Finally, the output of our function is how tall the plant is when it reaches maturity. Then the partial derivative of this particular function with respect to x is how much should the height change if I only change the amount of intensity of light it's receiving, and I hold all other parameters constant. I compute this partial derivative by trying to take the partial derivative with respect to x, which means I just take the derivative and I pretend like y is a constant and z is a constant. So the first derivative rule I use is the difference rule, or basically I just distribute the derivative. For the first term, I use the chain rule. I happen to remember that the derivative of secant is secant times tangent. When I use the chain rule for the stuff on the inside, I keep the inside part the same. So I have an x squared y and x squared y inside my respective trig functions. And then I have to multiply the derivative of the inside times the derivative of the outside. Similarly, the derivative of this outside function, derivative of tangent, is secant squared. So I just copy the same inside stuff into the secant squared. And then I multiply it times the derivative of the outside. Then I multiply it times the derivative of the inside, which is over here. Taking the derivative of the polynomials is relatively easy. I treat my y as a constant, but because my partial derivative is with respect to x, and my x is an x squared, so that is a power rule, which is why I get a 2xy over here. Similarly, on this term, I also have like a polynomial with a power rule of x cubed, and every other variable is treated like a constant, which gives me this expression over here. And I interpret this partial derivative with respect to x to tell me how much I should expect the height to actually change if the only ingredient in this growth I'm changing is the intensity of light. I can ask, well, how much does the fertilizer affect the height of the plant, by just saying what is the instantaneous change of the height with respect to just the amount of fertilizer I give it. So we take the partial derivative with respect to y, and we start by using the same difference rules we did before, so distribute the partial derivative to each term. And then we notice we have to use a chain rule. And the outside derivatives for the trig functions are the same. So the first term I get is secant of the stuff times the tangent of the stuff times the derivative of the inside, except this time it's the partial derivative with respect to y. For the second term I get a secant squared of the stuff times the partial derivative with respect to y of the inside. The resulting partial derivative of the inside is pretty straightforward. It's just a polynomial because it's just a y over here. I treat my x squared as a constant relative to y. Then I get an x squared as a factor outside. Similarly, I have a y over here, so it works the same way where every other variable is just treated like a constant when you take the partial derivative with respect to y. And this is telling me that if I want to know how the height of the plant is affected by the amount of fertilizer at any moment in time, I just change my fertilizer a little bit, I can expect the corresponding change in height. Similarly, if I want to know the effect of just changing the amount of water received by the plant is on this possible height when it reaches maturity, then I can go ahead and take the partial derivative of the measurement of the height function with respect to just z, or how much water it's getting. Now, I kind of skipped one of the steps because we've seen it a couple times. I just distribute the partial derivative with respect to z. And I do that because in this particular case, you notice that this term does not have a z variable here. So when I take the partial derivative with respect to z, everything else here is constant. And you take the partial derivative of basically a constant, you're going to be 0. I get the resulting partial derivative, and that's pretty much it. It all works the same way, you just have an extra variable, and you can use words to interpret what it means.